So, a very good afternoon to all of you, and this is the second session of the third day of ongoing STC on computational methods and analysis for engineers, organized by Department of Chemical Engineering, NIT Jalandhar. I am Dr. Rajkumar Arya, Associate Professor in Department of Chemical Engineering, is the course coordinator. Dr. Anurag Kumar Tiwari is the convener of the course, and the Dr. Sangeeta Garg is the patron and the head of the department. So the speaker of this particular session is Dr. KNS Kasi Viswanandham. So let me introduce you all to the speaker. We have amidst us Dr. KNS Kasi Viswanandham, who is a professor of mathematics and chairman admission at National Institute of Technology, Warangal. Dr. Viswanandham has a luminous academic record, having completed his BTech, uh, PhD from IIT Bombay, and postdoctoral fellow from IIT Madras. Prior to that, he completed his MSc in Applied Mathematics from REC Warangal and was a gold medalist. He completed his BSc from Nagarjuna University. Dr. Viswanandham has written two textbooks, published 45 research papers in international journals, and presented 5 papers in international conferences and 35 papers in national conferences. He is also the reviewer for several journals, which includes Numerical Computing, Mathematical Sciences, International Journal of Applied Science and Engineering, Mathematical Analysis and Modeling, Application of Applied Mathematics, Applied Mathematics and Computational, International Journal of Engineering Research and Technology, among others. Dr. Viswanandham is the life member of Indian Society for Technical Education, Andhra Pradesh, Society for Mathematical Sciences, Indian Society for Industrial and Applied Mathematics, and Indian Society for Theoretical and Applied Mechanics. He has guided 8 PhD students and 47 MSc dissertations. Dr. Viswanandham has been awarded the Best Citizen of India in the year 2010. He also received the Bharat Ratna Indira Gandhi Gold Medal Award in the year 2019. So, with this short introductions, I would now like to Dr. Viswanandhan to conduct the session. Over to you, sir.
Right. So thank you, Dr. Rajkumar Arya, for your brief introduction about me. First, let me share my talk. Sir, is it visible?
Yeah, it's coming.
Yeah, just 1 minute. I'll share this biggest PowerPoint and everything. It's a Wacom tablet also. Let me wherever I want, I can write also.
Yeah, and at the last of the session, you have to train also how to use that vacuum tablet.
It's a very simple, sir. Very simple. Yeah.
Yeah.
So here that pen and everything I can underline and I can do whatever I want. I can.
Yes, yes, yes,
Yeah,
yes.
yeah. So actually, first of all, I will let me thank the organizer, Dr. Rajkumar Arya, for giving the opportunity to speak in this webinar. Uh, when he contacted me uh, to give the talk on numerical differentiation and numerical integration, and then I asked him what are the type of the audience. Based on the type of the audience only, I can deliver the lecture and everything, my preparation, everything. He said that it's just like the classroom type. You can go ahead, sir, and think that step by step, if you explain, it will be better. That's what he suggested me. So based on that, I prepared about 38 the word files and everything. Then I converted to PowerPoint, and then I'm presenting here. Okay, so here,
Yes, actually, thank you very much, sir, for that. Actually, because we want our these participants to learn and use these things. Actually.
yeah. That's why I prepared at the. I thought that these are the BTech level students or MSc level students. In that way, I prepared and everything, sir. It's a minor level at the bottom. At the minor, I am prepared and then I am presenting. Sometimes it may be minute. Maybe some of the people may be knowing about this also, but my preparation is that how to concentrate on the errors and everything, which method we have to apply, at what occasions we have to apply, and how to take care of all those things. And if it is not there, how to take care of that. All those things I'm concentrating in my talk. Okay, sir. So now, so whenever numerical differentiation, why the numerical differentiation is necessary? For example, whenever a function is available, fx, so function fx is there. So if that function fx is there, automatically we can take the derivative, the expression, because the explicit expression for this function fx is available. We can go for the derivative. At any point, there will be fx is defined in that range, and the derivative also defined in that range. So at any point in that range, we can go for, so based on this, just if you take integrate derivative, we can get that. So then at any point in that range, we can evaluate this value. Okay, fine. So this is when the expression fx is available to us. Suppose if the fx expression is not available, only the function of fx is available at some point. That means x1, x2, etc., xn, or x0 to xn. So only at n plus 1 points it is available. The information is only available, the function values only, but no expression for this fx is available. But still, we want to get f dash x evaluated at any point in the range or at the given points. So what will be that? And if what are these points? So these are two types of the points are there. One is the evenly spaced points. The evenly spaced is the step length between the successive points is the same. The step length is same, or otherwise unevenly spaced points, or otherwise. So here, whatever it may be. So at any point other than these specified points also, we have to get the derivative. Then how to get all those things I'm covering in my talk in the numerical differentiation. Okay, so now let us see that. So these are, first I will concentrate on the equally spaced arguments, later I will concentrate on unequally spaced arguments. Now when the arguments are equally spaced, the function points are known to us, only the values are only known to us. That means f0, f2, etc., fn, these are only known to us, given at the points x0, x1, x2, etc., xn. Now our aim is to find out the values of, that means it's not exact value, at least approximate, that means numerical values of the first derivative of x, second derivative of x, etc., at a tabular point, the xi, without finding the actual expression for the fx, or fx is approximately px, where px is the interpolating the polynomial for the given data. So I hope that all of the readers knowing about the interpolating polynomial, with that understanding, I'm proceeding further. Okay. Now, when the px, we are not finding the actual expression for px also, but without finding the px also, now we want to get just using the differences, because these are equally spaced arguments. We can define the three types of the differences: the final differences, the forward differences, the backward differences, and then central differences. So how to use those differences and getting the derivative, this one. So derivative at a particular tabulated point. Now let us look at. First, I will concentrate on the forward differences. So derivatives in terms of the forward differences. Now we have the delta, that this is the delta is the forward difference operator. This is the triangle delta is the forward difference operator. For this forward difference operator, it is given by the step length h. That means here, these are, whatever is this is, it's there with the step length h we are taking. The arguments are equally with the step length. That step length h we are taking. So this is delta of f of x plus h minus fx. The difference, whatever it is, this is called the forward difference of fx. Now by Taylor's expansion, we can have this f of x plus h. Now this is the Taylor's expansion we are having. So for this one, if I use the operator, the operator d, which is identically equal to d by dx, right? So now this f of x plus whatever is there, that can be written like this here. So this is the one. So we are having, this is like this here. So we are having like this. Now here, if I take all these things operated on fx, so let me take the operator 1 and then on fx here. If you look at this expression here, 1 plus hd plus h square plus d square, h square is the hd whole square. Next term it will be h cube d cube by factorial 3. That is nothing but hd whole cube by factorial 3. It is looks like that the Maclaurin series expansion per e power hd. So what is the e power x we are having the Maclaurin? That is 1 plus x square by factorial 2 plus x cube by factorial 3, like that we are having. So in plus of x, now we have hd. So it will be e power hd. What is this expression? Say that expression is e power hd. So f of x, which is whatever is there, that is e power hd operate upon f of x. Now, whatever this expression 1 is there, so that delta of fx, let us take that one as, if I substitute, so this is f of x plus e power hd of f of x. So then if I take f of x as common with the operator, e power hd, the minus 1 we are going to get. Now here, because delta, suppose here if I write f of x here, I am going to get f of x here. If I write g of x here, g of x will come. If it is some other type, p of x, here p of x, whatever it may. So this is a dummy one for us. So the operator delta, it is identically equal to e power hd, the minus 1. So that's what I written. Now from this, the delta is, e power hd is 1 plus delta. Now for this one, if I take the logarithms on both sides, for this one, I'm getting this hd is equal to logarithm of e to the base e 1 plus delta. Now once again, if I use the operator here, this is Maclaurin's expansion for logarithm of 1 plus delta, if I'm getting this expression. Right? Now from this, our interest is to get, so our interest to get this one only. So d only, that means operator d, not hd. So take this h on the other side. Now we are going to get this. So this is the d. So that means if I apply this d is the operator. So if you apply on some factor, here same thing we have to get. So that's what I have taken in the next slide. So here you can see. So here f dash x for dfx f xi. So it is nothing but df at xi is f dash x. That means df at xi. That means it is f xi. So f of x at xi means f xi. So f xi we are taking in the picture. Right? So f of xi we are taking the picture now. Now you can see this is number dfi and 1 by h into this. F of x is fi. Now this is nothing but hd. So that will be this one here. So we are having HDs like this here. Take this HD. For example, if you take that HD on the side, already this we have taken HD. Once again, I am writing for some purpose. So this is first derivative is given by this expression. In this one, how many terms we have to retain? That means one term only we have to retain, or two terms we have to retain, three terms we have to retain, four terms we have to retain. What happens if you retain? That suppose if you retain only the one term, the rest of thing is the error, because ignored terms are the errors. Suppose if you retain the two terms from delta cube onwards, we have ignored, that is errors. What is going to be the error term and everything? That we'll see. So how much we have to retain and everything, that we'll see later. First of all, let us concentrate on the second derivative also. Later, I'll come to that now. So first, let us take up this here. So when hd is there, so various expressions. Now h square d square. So that will be, this is nothing but hd whole square. So that is this term whole square. Now various terms of this, if I take that, so many subsequent terms are there. Then what will be the expansion of these terms, the various terms? That means suppose if I have x1 plus x2 plus x3 plus etc. xn, n terms are the square of that I have taken. We know very well for two terms, three terms, four terms. But what about any number of, enlarged number of terms are there, how to take the square of those terms? For this one is very, very simple. But the only thing is that here individual terms square you take up, and then the combination of all second order combination, two terms combination. That means 2 into x1, x2, 2x1, x3, 2x1, x4, 2x1, x5, like that. 2x1, xn, the combination. And then 2x2, x3, and x2, x4, x2, x5, like that. You take the combinations and everything, and write finally the last term, it is 2xn minus 1 xn. That is the one. See, that way we have to expand. Now, if I expand on all those things here, let me take up the squares and all those things, and then cross terms. We are going to get delta square, minimum term square of this is delta square, and with the cross terms I can get delta cube, and here delta power 4, and the square of from this also I'm going to get delta power 4, like this I'm getting, and here delta power 5 with the square terms I'm not getting. But whereas here with the cross terms of these two, I will use some other pen. So here the cross terms of these two, delta power 5 is coming, delta square delta cube is also The cross term is coming here. So I collected all those coefficients and everything. This is the one, right? And finally, this is expression. After evaluating these values and expressions, finally we got this one. That means this h square d square is this. So d square is this. So d square fi is operated upon this. We are going to get this one. That means for the first order derivative, this is the expression we are having. For the second order, this is the expression we are having. The expression number 2 is for first order. Expression number 3 for the second order. Now, in these expressions, how many terms we have to retain? Let us look at that. So for that one, let us look at this one now. Right? Now we have seen this delta is additive to this. So by using the Macton's expansion for e power hd, finally we are going to get this. Now here, if I take the square of this, delta square, if I want to write, then the square of this I have to take up. So just like what we have done, the various terms and the combination, finally we are going to get like this here with the combination. This is a cross term, and this is the one I'm going to get here. And this is also with the square terms I'm going to get this. So collecting the coefficients and everything. So like that, the square of this, and then cross term of this, and the h power 4, d power 4 from the cross term of this, and square of this, collection of the coefficients. And finally I'm getting this is the one. So if you look at this here, when we are having delta, it starts with hd. And with the delta square, it started with h square d square. Now, if I proceed further, delta cube, if proceed, that means square of the cube of this term, if I take, it starts with h cube d cube. Now, if I take delta power 4, it starts with h power d power 4. Later, many terms may be there, but the first term is h cube d cube, h power d power 4, like this it will come. Let us take up. That means if I take the delta power 5, it starts with h power 5, d power 5, etc. That means like this it comes on. So let us look at that. To keep this point in view, let us go ahead further. Right? Now, if we ignore the terms of the term in 2, that means this is the one we are having. What is this? So here dfi, whatever you have, this is 1 by h of delta square by 2 plus delta cube by 3. So this is the dfi I am writing, because it is the previous slide, it is there. I'm writing once again. This is the dfi. It is equal to 1 by h of, this is delta minus delta square by 2 plus delta cube by 3 minus delta power 4 by 4, etc. operated on fi. This one. So if I retain only the first term, that means only up to this term, this neglected terms, whatever error, that is error. Now for this delta square expression, we've seen that first term is h square d square. Here h cube d cube, like that it comes on. Next term it will be 1 minus 1 by 4 into h power 4 d4, etc. It will come. Okay, whatever it may be. Now outside all these terms, I'm having 1 by h. Now if I take this 1 by h to each one of the term, so here it will be the dominating term is this here. It means 1 by h square d square, this 1 by h into h cube d cube, like this will come. So here if it will be the dominating term is this. So next term it will be h square d cube into something that will be there, some coefficient will be there. Plus next it will be h cube with some coefficient. This h cube d power 4, like this, etc. When h is very small, this h square, h cube, these are not the dominating. This is the dominating term. So due to this dominating term, so here this is the order of the h. That means when we retain a first term, we are getting the error is of order of h. Now if I take up this one here, if I retain the two terms, here, so in this expression, two terms, the error is this. That means delta minus delta square by 2. The error is this. Now error, this is h cube d cube. Now h power 4. The dominating term is this. So this is order of h square. Like that we are getting. Now what is this we have seen? When we retained only first term, order of h. When we retain the two terms, order of h square. Like this, if I proceed further, in general, 3 terms if I retain, order of h cube will be there. 4 terms if I retain, order of h power 4. In general, if we retain m terms here, order of h power m will be there. So this is the expression for the derivative for m terms here. So this is going to play a key role in this one. That means in various depressions and everything, when H is very, very small, that how much concentrate we have to give, as much as possible. Let us take up. Let us not stop with one term, two terms, three terms. Generally, the people will stop with this one term, two term, three terms. Okay, fine. But if we want the accuracy, when H is 0.1, up to from this delta power H power 4, that means 3 decimal accuracy is coming. Suppose if you stop with this one, it is only up to first decimal only accuracy is coming. From the second decimal onwards, the error is coming. But I don't want. So second decimal will be error. Even second decimal, third decimal is also, let us concentrate on this one. So then more accuracy is, sometimes more accuracy is required. So when the concentration is very, very minute, microns we are calculating and everything. So when you are using your values as the microns, then automatically your error also should be very, very less. So due to that here, it is more concentration I'm giving here. So how many terms we have to retain based upon your value of H, how much it will be. That means here, if you retain 3 terms, H power 4 means the whatever the difference error is coming, only up to 4th decimal the change is coming. That means up to 3 decimal places, the coincidence is there. If I retain the 4 terms, then up to 4 decimals coincidence is coming. So suppose if H is good 0.1, with that sense I'm talking. If H is still small, more accuracy will come there. In general, people will take not more than less than 0.1. Generally, the people will not take. In that sense, I'm talking about this. So this is in terms of the forward differences. The same way, let us go ahead with the backward differences. So Dr. Arya sir, is it okay, sir?
Yes, sir. Yes, sir.
Yeah. Now,
it's fine.
Yeah. Now with the first derivative I have taken up. Now let us look at the second order derivatives. So second order derivatives, how many terms we attend, what will be the order of the error and everything. Let us look at that. So suppose this is the expression for the second order derivative. Already this is in the chemistry. Once again, I retaped here. So if we retain only the first term, that means only up to this term only if we retain. And this is the error we are going to get. So that is error. Now once again, you know this is H cube D cube, is H power 4 D power 4 like this. Now the order of this will be order of H because already 1 by H square is there. Here H cube means H. And here it will be H square, 1 by H square into H power 4, H square. So here H, next term is H square, next term is H cube like that. So dominating term is H here. That means if you retain only one term, order of H is only coming. So like this here, if I take the 2 terms, it is coming starting with the error is delta power 4. So 1 by H square is H power 4. So H square. So order of H square is the error now. So like this here, as in the first order derivative, here also, if you retain the m terms, if you retain the m terms, the error is of order H power m. So this is the one. So this is in terms of the forward differences, right? So now let us look at that. So let us go ahead with the backward differences. First, let me define in terms of forward differences, backward differences, central differences. Then I'll take some examples. Okay. Now, which one we have to take up? That also I will explain. First, let me take up the expressions with what errors is coming for every time. Let us look at that. So now if I take the backward difference from the present point, if I take the backward difference here, if I take the derivative here, so that this is a backward, this is a forward difference operator, this is a forward difference operator, and it is reverse. Always the backward is a reverse to forward. So the triangle delta, whatever it is, it is reverse that is del is the operator del. This is used for the backward difference operator. So that means from the present step, you move one step backward and then take the difference from the present one. So this is the one. From the present step, you move backward. Always from the higher to lower level only the difference should be taken, not the reverse case. Here, higher to lower. X is the first point and lower point is X minus H. So higher to lower. And even the earlier also we have taken. So in the forward difference here, delta of Fx means, so F of X plus H and minus F of X. So when you take the X plus H and Fx, the higher level is X plus H when compared to H. So always the difference, first we have to write as higher level. Later, the lower level. In that context only, always the difference should be taken. Higher level, lower level. That is the main point here. So higher level to the lower level, we are taking the difference. Now here, if I use the Maclaurin's expansion for this, or Taylor's expansion, Taylor series, not Maclaurin series, Taylor's expansion for this f of X minus H, we are going to get this. Now taking the operator D, and we are getting, this is a 1. Now this is the Macron's expansion of e power minus hd. This is expression whatever is there, e power minus hd. Now this is it. This is whatever is there, this f of x minus h. Let us substitute in this expression. Now this will be fx minus the del of fx here. So let us del of fx minus e power minus hd into f of x. So if I take fx as common and 1 minus e power minus hd, this is the operator for f of x we are having. Now this is del operator upon fx, we are getting this. If gx is there, gx will come. If hx, some px is there, px will come. If qx is there, qx will come. Like that. So the operator del is identical to this. Now for this, from this, I can get e power minus hd is this. Now, if I take the logarithm for this, minus hd is this logarithm. So Macron's expansion, if I use this one. Now from this, I'm going to get this one here, the operator d. Now d operator in fi, it will 1 by h into this. This is the first order derivative expression. Similarly, this is hd, whatever is there. So this hd is this one. From this, I'm getting this hd, right? Now this is the one. So and then we have h square d square as we have done in the forward differences. So like this, I'm getting here. This will be h, taking the squares of terms, cubic terms, and everything. The starting one is here. This one, h square d square is del square, h cubed is del cube, h power 4 is del power 4. Like this, we are going to get here. So this is the one we are going to get. Now let us take up here. Also we have del is this, then del square is this one here. So like this here. So del square is h square d square, squaring of all these things here we are having. So squaring is this one. First term is h square d square. And if cubing this one, we are going to get h cube d cube. Fourth term power if we take up h power d power 4. Now for the expression we are having, the whatever this del of fi on this. So in this one, if I operate on fi, so this is operated on, this is the one. This will be this one. This is dfi. So what is dfi in terms of backward differences? This is 1 by h into, this is del plus del square by 2 plus del cube by 3, etc. This is operated on fi. So this is the expression for derivative in terms of backward differences. Suppose if I retain only the first term, so that's what I have taken. The error term is from this onwards. Now once again, del square is h square d square. Del cube is h cube. If I substitute and everything, finally we are going to get this order of h. That means when you retain only up to the first term, order of h is the error. Now if you retain only the first two terms, that means these two terms if you retain, so then from this term onwards, the error is coming. So from this term, it is error is coming from this one here. You can see. That means two terms we are retaining. If we are retaining up to two terms, means the error is coming from this term onwards. Delta cube onwards. Del cube onwards, the error is coming. So now once again, if you substitute h cube d cube here, h power 4 d power 4. So finally, this h square. So in general, we are having n terms if we retain, order of h power m will be the error. So this is the one we are having. That is more important. That means how many terms we have to retain. Now let us keep all these things in our mind and let us go ahead. The same way for second order derivative. If I take up this one, the same thing here. You can see like this. In general, if you retain m terms of backward difference, the order will be h power m. So this is the one expression. For this expression, the second order derivative, if I take up, so m terms if I retain, I'm going to get order of h power m. All these things, forward difference, backward difference. Now let us look at the central differences. Sir, is it okay?
It's fine.
Fine,
It's
sir?
good actually.
Yeah.
Yeah, it's going good.
Yeah. Now let me take up this. So derivatives in terms of the central differences. Right. So define the shift operator E. It is nothing but e power k f of x is x plus kh f of x, where k need not be entered. It can be any value. The positive, negative, and fraction, anything, whatever we want, we can have. This one here. Just 1 minute, please. Yeah. So this is k need not be an integer. It can be fractional, half, 3 by 4, something, anything it can be. Now in this one, if I take the delta of fx, that means it's center. That means this point x, that is center. When it will be center, half step forward you take up, that is h by 2. Half step forward means from x, if you take half step forward, x plus h by 2. And from x, you take half step backward. Now, from the arguments we are having, x plus h by 2 is one value, x minus h by 2 value. From higher to lower, we have to take the difference. Now, let us take. This is a central difference. Now, let us use one more thing. This is mu of fx. That is the average operator. This mu is nothing but this is the average operator. This is the average operator. Right? If I take the average operator here, this will be, that means you, from the point x, you move half step forward, half step backward, and then take the average. So for those two values, function values, you take the average. This is the average operator and center difference operator. Center difference average. So now let us take up this here. Now let us consider this one. So I'm going to take up this. So delta of fx is, so this is based on this definition, whatever you have, the shift operator. So here it looks like this express h, this means your k is equal to half here. If I just compare with this, your k is equal to half. So e power half fx here. Now when I here minus half into h, that your k is minus half in this case. K is minus half in this case. So let me write this one. Now in both the places, fx if I take as common, now this is e power half, e power minus half. So if fx is there, fx will come. If gx is there, gx will come. So with that understanding, your operator delta, it is identically equal to this one here. That is the one we are having. Okay, sir? So in the same way, if I take the average operator, mu of fx is concerned. So same thing. So it is a e power half and e power minus half. So I take up that fx and then take the operator. So that is operator, this mu is nothing but, so this one here. Now we have the two things here. So from this, take this 2 on the other side, 2 mu is this here. So 2 mu is equal to e power half plus e power minus half. And whereas the delta operator, this is the one. So two things we are having, 1 and 2. This is 1 is important. This 2 is also important. Let us look at that one here. Now, if I take up this here, the square of this, that is 4 mu square and minus delta square. What happens to this? This is e power half whole square, e power minus half whole square, and here delta square is different. This is in the looks like form of a plus b whole square, a minus b whole square, a plus b whole square minus a plus b whole square means 4ab. So that is e power half. So this will contribute 1. So this will be 4. Now that means here we are having 4 mu square minus delta square is 4. So take this delta square on the other side and then divide by 4. We are interested in the mu square only. So take this delta square on the other side, that is 4 plus delta square. So mu square is nothing but 4 plus delta square divided by 4. So this is the one. So now if I multiply this one and I'm going to get this is 1. That means mu square is identically equal to 1 plus delta square by 2. Whenever we want, we can apply this. This is more important for us. Okay. Now we have the mu delta. So mu delta, if I take the mu delta, it is half into e power half plus e power minus half and this one. This is a plus b into a minus b. So a square minus b square. So that a square means that is e, and here b square means e power minus 1. So let us take up that. That means your e, this is nothing but here, this is the one we are having. So e of fx is already we have this one, sine e power hd of this one. So let us take up that one and let us use that. So that e power minus 1 means for this one, if I take e power minus 1, e power hd minus 1, suppose if I take this one here, this is minus hd will come here. So for this one, e power hd and this is e power minus hd. That's what. So this is nothing but the expansion. This is nothing but the hyperbolic expansion for sine hyperbolic hd. So from this mu delta, if I apply the Maclaurin's expansion for this, just 1 minute, please. Previous one. Yes. If you apply the Maclaurin's expansion for this, I'm going to get. Or otherwise, if you use the Maclaurin's for e power hd, e power minus hd, whatever it may be, either for sine hyperbolic hd or for this, you apply that, and then finally the result is coming this one here. This is the one. Mu delta is equal to the equation number 7. Now let us go to this one here. Delta square. So this one square of this. So this one here. So e power hd is 1. If I use the Maclaurin section, finally I'm going to get this one. Delta square is like this. Now using the previous expression number 7 and 8, finally I'm interested in mu delta cube. That is mu delta into delta square. So mu delta is just now this, and delta square is also we have evaluated, and take the cross terms of this. If I take up this one here, so we are going to get higher from higher terms of this. So cross terms of these two, and here this will be these two cross terms h power 5 d power 5, or these two cross terms I'm getting h power 5 d power 5 collection like this. So minimum term is h cube d cube, next h power d 5, like this higher terms will come. Okay, let us find. So this is the one I'm getting mu delta cube here. Now delta power 4, this will be. Why I'm taking all these things here is that in the center, whenever you use the center difference operator, we are going to get mu delta, second order delta square, third order mu delta cube, fourth order it will be delta power 4 and mu delta power 5, and here delta power 6. That means in the central difference operators, when you are using the odd powers, orders of the central difference, it is average operator is combined with that here. You can see odd orders of the central order difference, so it is average operator is combined. In the expansions of the this one interpolation polynomials and everything, if you take that, this picture will be very clear. Now suppose if I take the even orders of central differences, no, directly we are going to get here like this here. That's why we are interested. This is what is mu delta, what is delta square, what is mu delta cube, what is delta power 4, what is mu delta power 5, and what is mu delta power 6 in terms of the our derivative operator we want to get. Why we are getting all these things in this particular manner only? This is a reason, because in the interpolating expansion of the center in terms of central differences, so we are going to get a Sterling's approximation or Gauss forward approximation or Gauss backward approximation. Three different expressions are there for a central difference interpolating polynomial. So all those things we have these things only here. So let me take up this one here. So like this here, delta power 4. Delta power 4 is delta square whole square. So this one. Now if I collect, we are going to get like this. Now here, if you look at this here, mu delta, it started with hd, delta square h square d square, mu delta cube, h cube d cube started with, delta power started with h power 4. In that manner, mu delta power starts with h power 5 d power 5. Delta power 6, it starts with h power d power 6. Like this, we are having this one here. Now, let us look at the Maclaurin's expansion for h sine hyperbolic h inverse x. Sine h inverse x of this. This is Maclaurin's expansion. Because we have the sine hyperbolic hd is equal to sine inverse. Because we have earlier mu delta is equal to sine hyperbolic of hd. Now from this, what is your hd? The sine hyperbolic inverse mu delta. So let us apply the Maclaurin's expansion for this. This one only I have written here. And then Maclaurin's expansion, in place of x, we have mu delta, if we apply. Now, once again, we are always, it is expressions in terms of derivatives available, mu delta cube, mu delta 4, not mu cube delta cube, mu power 5 delta 4, not this one. So let us write once again, this mu cube split it into mu square. And this will be mu power 5. This is mu square whole square. Already mu square, that is 1 plus delta square by 4. We have seen that mu square is equal to 1 plus delta square by 4. This we have seen. So let us use that one now. Okay, if I apply that and here the square and then collecting the like coefficients and everything after expansion, everything, if I collect the like coefficients, so this one expansion of this a plus b square like type. Then if I collect the coefficient here, this is 1 in delta cube, mu delta cube. Here it starts with the delta power 5 from here. You can see it is delta power 5. And here delta square into delta power 5 is coming, the collection and all those things if you look at that. So like this we are having. So this is the one hd is this here, you can see. And in this average operator, this is delta, when delta cube, all this, whatever it may be. This is for our understanding purpose. I have taken like this here. Actually, original one is this and this is one. That means from this I can get that d is equal to 1 by h of this one, whatever we are having here. Okay. Now let us look at this here. Suppose if I take up h square d square, because hd is mu into this one, mu square d square. So this will mu square is 1 plus delta square. For this square terms, if I expand this, I am going to get this. Now once again, if I collect the cost terms and everything, if I take the multiplication of those two factors, finally we are going to get this. So from this h square is this one here. Okay. Now in these expressions, either hd or h square d square, we are having some, in terms of central difference operators, we are having how many terms we have written. Just like as in the case of the forward differences and backward, how many terms we have written. That we let us see. Suppose if I take HD is like this here. So this already I'm giving once again that expression already what we have seen. From this D is this. So D of Fm is 1 by H into this. If I retain only the first term, the error is from this term onwards now. So this is error. So that is error. Now from this error, I'm getting the dominating term is this here. So this is H cube D cube. But already we have seen mu delta cube is having H cube D cube. So 1 by 6 H will be, so H will be. Next it will be mu delta power 5 will come. So that will be H power 4 D power 4. Because H is there, H power 4 D power 4. Like this it will be. That means if you retain only the one term here, H order of H square is coming. Suppose if I retain the two terms, here order of H power 4 is coming here. Order of H power 4 is coming. Let us look at this here. Okay. So now like this here, that means if you retain the one term, order of H square. If you retain the two terms, H power 4. If you retain in the same manner, if you retain three terms, order of H power 6. If you retain the four terms, order of H power 8. That means in general, if you retain the m terms here, order of H power 2 power m will come. Whereas in the forward differences and backward differences, if you retain the m terms, we are getting the error is only order of H power m only. But whereas here, H power 2m, that is more important here. That means with less terms we are retaining, but error is coming. If we use the forward differences or backward differences, to get the order of H power 2m, we have to retain 2m terms. But whereas here with the m terms only we are getting. With less terms, more accuracy is coming here. The error is more. Error is less. More accuracy is coming. So that is with less terms, more accuracy. That is more important. Always computational comprehension, not only taking the errors into consideration, computational comprehension with less terms we have to use and more accuracy should come. There the computational complexity will come here. So with the less computational effort, we have to get a more accuracy. That is a more important here. So that's why with the less terms, we are getting the more accuracy. So that is more. Okay. Now in the same way, if I take the expression for H square D square, so this will be this one. If I retain D square Fi is this, so retain the first term. So I'm getting only the error is order of H square, just like as in the case first order derivative. Now if I take the second two terms in this one, now I'm going to get here order of H power 4. In general, if I retain the three terms, order of H power 6. If four terms, order of H power 8, like this. So if you retain the m terms there, it will be order of H power 2m. Now all the terms expressions are available. That means for a particular derivative, in terms of forward differences we can write, in terms of backward differences we can write, in terms of central differences also we can write. Anything, all of the things we can write. So now how to take care of all those things. So let us look at this. A small, before going to the example, I want to give one this thing here. Suppose if I write f of I plus 1 minus fi. From the point I, if I look at this, I moved one step forward and then we have taken a difference. So this will be with respect to the fi, it is forward difference. Now if I look with respect to the point I plus 1, we moved one step backward and we have taken a difference. With respect to view, view is important here. From which point you are viewing, with respect to point I you are viewing, or with respect to point I plus 1 you are viewing. That is more important. From which point you are viewing the difference. So if we are viewing the difference from the point I plus 1, we moved backward and we have taken a difference. So this will be the backward difference of fi plus 1. Now I did not view either from I plus 1 or I in between center. So this is delta fi. That means from the ith point, we moved half step forward, half step backward, and then we have taken difference. From I plus half step forward means I plus 1. From I plus half step backward means I. So that this is the one we are giving. That means from which point you are looking this difference. The difference is the same. But we have written the same difference into the forward difference, backward difference, and then central difference. Only view is important. So that's what we are. So this is more important. Viewing is more important. That means always we are taking the difference of the two values. But we can write in terms of all these three, and we can go ahead like this here. So that will be. Suppose if we take the second order difference here, Fi plus 2, right? And here 2 into Fi or Fi plus 1 and Fi. From the point I, if I look at this, the second order forward difference, from the point I plus 2, if I look at this, this is the center. This is delta square Fi plus 2. From the central point, because 3 points we are having, I plus 2, I plus 1, I. From the center point, if I take here, this will be delta square Fi plus 1. So like this, some differences, all these are the same differences we are having. But something different here. All the three we can write, nothing wrong in that. So that I'm taking with this one, I'm proceeding further with the example. Now you will get very clear picture about this one here, why I'm using all these things. Now let us look at this here. Just I'm taking this here. Find the first order derivative or second order derivative at the point 1.1, 1.6. This is the data we have given. 1.1, 1.6. These are the tabulated points. First, I'm considering tabulated three. Later, I will take up the non-tabulated points. So first, let us look at this here. Now, if I take the difference, this is the y of x means, or y or f. It does not matter. Same thing. If you want to, you can take y also, f also. It is only for our understanding purpose. So here, y defined at x0 is y0. Y defined at x1 is y1. That means this is our y0. This is a defined at y1. This is y2. Like this, I am having. This is y6. Y defined at x6 is y6. Now, if I take difference of these two, y1 minus y0 here. Y1 minus y0. This is one. In terms of forward and backward, only I have written. Central I have not written. Okay. Okay. Now, if I take this one here, difference of these two, y2 minus y1 is one. This is y3 minus y2, like this here. Now, if I take the difference of these two, now this is the one with forward, backward, like this I have taken. Sir, is this table is clear, sir? Hello?
Yes, sir. Yes, sir. It's clear.
Yeah. So now how I have written, just I'm leaving only the idea how I have taken both forward, backward, all the things I have written. Okay. Now, if I want to evaluate at a particular point, xi, this is the forward difference. So, in terms of forward difference at a point xi, that means yi is coming here, and this is in terms of backward differences. This is in terms of backward difference. This one. Now, let us take up at x is equal to 0.1. X is equal to 1.1. I want to get the forward difference. That means this one. That means at y1. If I look at this here, that means here y1, delta square y1, delta cube y1, delta power 4 y1, delta power 1. That means 5 terms of this one I am having. Suppose if I use the backward, only one term I am retaining. You can see. That means in these expressions, at x is equal to x1 means if I take this one, only I can retain up to 5 terms. And whereas here I can retain only up to this. That means if I retain up to 5 terms, the values are available up to del power 5. That means my error is at this derivative at the 1.1 is with this expression, it is order of h power 5. And whereas if I take with this expression, backward difference, I'm getting only order of h only. Now, because h is equal to 0.1, with the order of h power 5 means the error, now you can see up to 5 decimal places, it is matching. Whereas this one, here it is matching only up to first decimal place. So 5 decimal places is important for us. So we can go, we are going ahead. So like this second order also, if we retain. So you can see this. This is one. So second order derivative also, if I take up this one here, so second order derivative. So x1 is 1.1. So this is delta square y1, delta cube y1, delta power 4, all those things are there. You can see this at y1. Delta square y1 is not defined at all in this table. Only del y1, del square y1, only the second order is coming from y2. That it is not defined at all. So we have to use only forward difference only. Like this we are having. So like this forward, for axis it is backward is more important. Backward gives the more accuracy error. And like this here, you can see. So because this is at x1, this is at x6. Sir, is this clear? Which expression we have to use? Okay, now we'll take up the next one here. If x represents the speed of the vehicle, then find the velocity and acceleration of the vehicle at time t is equal to 0.1, 0.3, 0.5. 0.1, it is here. 0.1 is here. 0.3 is here. And 0.5 is here. Now let us take up into the forward, backward, central, everything let us take up. Here, the same difference here. This is at x1. This is x2. That means x0, sorry. Hello? Yes, sir.
Hello.
Yes.
Excuse me, sir. Yeah, suppose I have, let's say, 100 data points, something or more than that, because in my case of drying or polymeric
Yeah,
coating, if I
even
give more than means 1,000 data points
yeah,
actually.
yeah, but because here it is a simple. Yeah, yeah.
So in that case, suppose I want to calculate rate. Rate is practice.
Yeah, it is possible, sir. Just you can write a computer programming or
So
MATLAB or mathematics, anything, whatever you use. You can write a program also, your C or Fortran, whatever it may be. You can write a
mhm.
simple program. And here, for first order derivative, is simple expression here. The DFI, it is just nothing but 1 by h into this is a forward difference of r minus del square here my plus del cube minus del power 4 by 2 by 3 by power 4 etc. Even for 100 if we take up here del power this delta power 100 by 100 it will come here. That's all. It's very simple expression, first order derivative expression.
So I mean to say
Yeah,
that
you just using a
yes,
programming
yes, yes. So
and
if somebody is doing just to
and even into the backward if there's no minus sign will give me and same
yeah,
expression
in
with plus
case
sign will
actually
come.
somebody is calculating the
Yeah, if we could able to calculate with the given data 100 points, let him calculate
okay,
using the
okay,
programming. The programming manually it is difficult, but programming
correct,
it is
correct,
okay.
correct.
It will take care, no problem. If a fraction of a second will get the result. Only if the program executes well. No syntax error is there, no computation error is there, everything is going well. Just in a fraction of a second, we will get the result. So then accuracy is more important in that way.
Right, right.
And here I have taken up only h is equal to 0.1. Sometimes your h may be 0.6 also or 0.5, something like that. Even for those things also, if higher powers is available, you can utilize that. No problem. We can go ahead,
Yeah,
sir. No
correct.
problem. It's okay. Then higher terms required here. To get the more accuracy, higher terms are required here. With h is equal to 0.5, more terms are required. So then this will be useful. Only here I'm illustrating purpose I have taken which can be manually calculated. And sometimes if we are interested, you can write a programming also. Nothing wrong in that. Just logic wise I want to present here. You can extend. Whatever the number of terms you can extend. No problem at all. Okay, sir? So here, shall I proceed, sir?
Yeah, yeah, sure, sure.
Yeah, yeah. So here, then higher terms and everything like this, it is coming in terms of forward, backward, same difference I have taken up and I have written here. So all these things, first order, fourth order, up to sixth order, we are getting here. Now, if I want to take up the derivative here, so velocity, it is nothing but a first order derivative because this is a displacement. This is speed means it is nothing but speed of the vehicle, rate of change of speed or displacement, whatever it may be. So it is velocity and rate of change of velocity, it is the acceleration. That means first order derivative for x, it is represents the velocity. Second order derivative for the x, it represents the acceleration. So let us take up and then proceed. So if I take up these terms into the forward differences, this is a backward difference. Here, first order forward differences, backward difference, central differences. Here, this will be forward difference, second order derivative, forward, backward, central. Now let us look at this table. So where we want to get? So we want to get at the point 1, first order derivative. That means first order derivative is del x1 here. You can see. So here del x1, del square x1, del cube x1, del power 4x1. Like this we can retain. But whereas here backward difference is only 1 point. That means I cannot use the backward. Central, it is not there at all. You can see. So if I use the central difference here, you can see Here minus of is not, when I is equal to 1, it is only this one here. It is not there here. You can see. So like this we have to get. And you can see this one. Which one is better and everything. If you look at this, the forward is better, central is better. You can use that and get this one. So forward is better here. And you can see that. So I did not calculate, but here this is the idea how to calculate this only. I did not calculate, just I gave the idea. And here for the T3, central is better. For the T5, that means at a point, it is a backward is better. So in the same way, second order derivative is also. So for at 1.1, the forward is better. For the T3, central is better. And here better. So in this way we have to do. Okay. So this is the idea behind whenever we want to take up at the tabulated points. That means they are equally spaced. Suppose if they are unequally spaced, what is the guarantee that all the time the data of f defined at the points xi for I is equal to 1, 2, 3, etc. up to n. That means the points x1, x2, etc. xn. What is the guarantee that these points are equally spaced points? Sometimes they may be unequally spaced. Then how to get that one? So for that one, let us use the interpolating polynomial only. No other option left with us. We have to go for the interpolating polynomial. We have to get. Sorry, suppose if this is a tedious job to get the interpolating polynomial, then how to do? That also I'm giving. If you are in a position to find out the interpolating polynomial, let us find out the expression for it, p of x, and go ahead. Because fx is approximately equal to p of x. So the derivative of fx also is approximately equal to p dash x only. So at whatever point we want to calculate, let us calculate this one and go ahead. So like that we are taking up here. So now we are using at these points and everything. It is given. So here the given data, the arguments are, this is we want to find out the derivative. Yes. The 3, 5, 11, 27, 34. These are the points, arguments of x. The point, this is x1, x2, x3, x4, x5. These are unequally spaced. So we cannot use the forward difference, backward or central difference. So we have to go for interpolating because less number of points are, we are in a position to calculate interpolating polynomial. Suppose if the interpolating polynomial is not possible, then how to proceed? That also I'm taking up. So this is I'm using a divide difference, or in place of the divide difference, if you are interested, you can use the Lagrange's interpolating polynomial also. So whenever unequally spaced points are there are two types of the divide difference interpolating polynomials we can use, either the divide differences or Lagrange's. Whatever you take up, but interpolating polynomial is unique irrespective of whatever the formula you use. The final expression, the px expression is unique only. It won't differ from formula to formula. And that is unique one. So due to that, if you are interested, sir, I don't know about the divide differences. I know only Lagrange. Yes, you can use Lagrange's. Nothing wrong in it. You can get. But final expression is one and the same. There is no problem. So I'm taking this one here in terms of this one. So this is the formula I'm having. So if I use the values and everything from the table, finally I'm going to get, this is the one here. So this I'm getting the expression here. Instead of finding the expression and everything here, so I am taking up x cube, x square, x, and instead of evaluating, just I'll take up here the square of this. If I take the derivative, this is 3x square will come, and here 2x will come. Here this multiplied with this, that one. Straight away, the values of these will be available. Just substitute and get that one. That means here we are in a position to calculate here interpolating polynomial expression. Suppose if it is not available, then how to do? Let us take up that one now. Okay. And here, let me take up. This is the in terms of forward difference, backward, whatever it may be, because the interpolating polynomial is unique. Any one of them you can take up and proceed. So let us take up fx in terms of forward differences I'm writing, in terms of backward difference I'm writing, in terms of the central differences I'm writing. Nothing wrong. Whatever it may be, does not matter. Okay. Now in this one, suppose if I use here, that means when the arguments are equally spaced points, not at the tabulated point, and how to use that. If it is a non-tabulated point means we have to go for interpolating polynomial only, whether it is equally spaced or unequally spaced. Unequally spaced means interpolating polynomial of that one, divide difference or Lagrange we have to use. And whereas equally spaced, we can use the forward, backward, central. Let us use that. How to make it simple without you going for those things and everything. Let us just look at that here. In terms of forward this, backward this, central this. Now wherever you want to get here fx, it is in terms of x. So here the p, it is given in terms of s. What is this x? Yes here. Let x's be a point which is not tabulated. At that particular point, we want to calculate the derivative. So let us take s is equal to x minus x by h, where x is equal to sh. Now here, in general, x at different points we want to get. This may be a variable. We can take this a variable, not at a specific point, at some other point also, some other points also. Anywhere it can be range, it can be in our given range. So due to that, let us take this x as a variable and proceed further. So if we take this as one, in terms of that, yes, this is a forward difference one. In terms of that, yes, this is a backward difference expression. And this is a central difference expression. Okay. Now let us take up this one here. And based upon whichever is available from the differences you can use, and we can get this. So this dp by ds, because p, it is now given in terms of s only. So let us take up dp by ds and ds by, using the chain rule. What is ds by dx here? When s is equal to like this here, ds by dx is 1 by h into dx. So that will be 1. So ds by dx is nothing but 1 by h. So let us use that one here. So this is 1 by h I'm having, and then proceeding further. So 1 by h and dp by ds. Just for this expression, you take up dp by ds and proceed, and we'll get that one here. So here for this one, take 3.5, which is not a tabulated point, into the forward difference. This is expression I'm having, table I have calculated, and this is the one. And we are having, you can see. So s is equal to 0.5. Just substitute that value of s here. When you have this one, in terms of dp by ds, if you take, this is the expression we are going to get. This is the expression. Just to substitute the value of s, we are going to get this. Over. It's a very, very simple. It's a tabulated point and a non-tabulated point. Both we have taken. Okay. Sir, is this clear, sir? Shall I move to the next topic, that is numerical integration?
Yeah, you can move ahead.
Yeah. Now our aim is to find out the numerical value of the different thing. We want to find the integral here. That means whenever it is this is there, finally it will be some numerical value only. It is no more an expression, because it's a different integral. It is some numerical value. If your integration is easy, for this expression depends upon the expression of this by x. If it is integration easy, we can get the explicit expression for the integration of this, and then we can substitute the upper limit and lower limits, and then we can get. That means integration of yx is some dx. This is some g of x is there. That integration from a to b yx dx. It is nothing but g of x between the limits x is equal to a and b. Now this is g of b minus g of a. So when this expression is available to us, g of b, g of a, some numerical values. The difference of the numerical values is some numerical value. Finally, this is some numerical value. That means once if you know the integral of yx is known as g of x, it's okay. Suppose if some complicated expression is given for yx of x, then getting this gx is very, very difficult. But even then, even though we may not be knowing the actual expression for g of x, now if we are trying to get the numerical approximation to this value of g of b minus g of a, for this one, let us find out the numerical approximation. So that is, finding this numerical approximation is known as a numerical integration. How to get that one? Let us use that. Let us divide this interval a to b into some equal number of n intervals. So n intervals I'm dividing. So when I'm dividing the n intervals, so with the step length h, So the points are x0 to xn with step length h. That is x0, x1, etc., xn, n plus 1 points with n intervals I'm taking. With those n plus 1 points, if I take the interpolating polynomial for yx in this interval ab, so I'm going to get this is a 1. Because the expression for yx is available. But integration may be difficult, but expression is known to us. The integrand yx is known to us very clearly. Unless the expression is given, we cannot go for the integration. The expression yx is known, but gx may not be known to us. It may be difficult. But we can find out this numerical approximation for this g of b minus g of a. What will be the numerical approximation? That is our aim. So because the yx expression, the integrand yx is available, so now I can get y at x0, y0, y at x1, y1, y at x2, x, y2, etc., yn. So y0, y1, y etc., yn is available. Now I can find out the all the forward differences or all those things I can get, and I can get this expression here. This is the interpolating polynomial. Let us use this px in this one now. Because yx is approximately equal to px, then this integration also will become the approximation. It is no more a exact one. Now this is the one. Okay. Now let us use. Yes, I don't want to. In general, yes, we want to evaluate this integration very simply. So for that one, let us use this one here. So for this one, I'm having the various factors x minus x0 and x minus x0, x minus x1, and along with these two factors x minus x2. In the next, I'm having x minus x3, x minus x4 like this. I'm having. Once if I find these expressions, the factors of this x minus of xi in general, what will be that? Let us take up this. This is x minus x0, xi minus x0. So it is one simile. Another way I have written nothing else. This is plus x0. This is minus and plus x0. These two will get cancelled. Finally, it is the same only. So this is nothing but this one only, right? Just 1 minute. Yeah. Just 1 minute. Sorry, it stopped. Just 1 minute. Sorry.
It's okay, sir. No problem. Yeah. It happens actually.
Yeah, somehow.
Yeah, due to the network connectivity and so many issues are there.
Wrong command I have given. That's one.
Yeah.
The wrong command.
So if any participants have any question, they can ask in between also. No need to wait actually for the last actually. So whenever they have the question, they can ask.
Yeah. Yeah. So this is the one I'm having. So this one, if I substituted everything, and finally I'm going to get this, right? If I take n is equal to 1, that means only one interval I have taken. The interval AB is divided into only one interval. It is called the trapezoidal rule. And if n is equal to 2, it is known as the Simpson's 1/3 rule. If n is equal to 3, Simpson's 3/8 rule. If n is equal to 4, it is called a Boole's rule. If n is equal to 6, it is called a Wedley's rule. Sorry, n is equal to 4, it is Wedley's. And n is equal to 6, it is called a Boole's. Like that, various numbers and everything. But most familiar ones are these only. Trapezoidal, 1/3 and 3/8. Simpson's 1/3, Simpson's 3/8. I am concentrating only on these three and I am proceeding further. What happens when you take these things? What are the errors? How to get and everything? My concentration, which one is the most appropriate one out of this? If these are not, sometimes these are also may not be suitable. Some other one, how to take care. That one also I'm going to take up. Okay. So now let us see. If n is equal to 1, trapezoidal, if I'm taking this here. If n is equal to 1, only one interval I have taken. So then this is a 1. So S is from 0 to 1, it is I'm going to get. So this is the one we are going to get here. So just if you substitute, finally we are going to get this. Why it is called trapezoidal? So let us look at this physical interpretation of this. Generally, integration from A to B, yx dx, or this is nothing but A is equal to x0 here, and B is equal to x1 we have taken. And what will be this here? So if I take this physical interpretation of this here, x-axis, this is the y-axis. If this is a curve I'm having, This is a curve y of x, and this is a point x naught I'm having. This is a point x1 if I'm having. Now the integration of this with the points, this one, it gives the area of this one only. Am I right, sir? So this is a physical interpretation. That means provided this curve y is equal to yx, the curve yx does not cross this x-axis. It is not crossing here in this expression, in this figure. Okay, the area of this is physically, it is going to be given by this integral. That is a physical or geometrical interpretation of this integral. Okay, now if I'm taking this one here, that means here what is this? The step length between whatever this is h, and this is this line, whatever this is there. This is a point x naught, y naught, and this is a point x1, y1 we are having. That means this length is y1 and this length is y naught. Now if I consider these sides y naught and y1, these two are the parallel sides, and if I consider this a, b, c, d, this one, I'm take some other pen. This is a trapezoid or not? This ABCD, it is a trapezoid. So what is the area of the trapezoidal? We are taking area of trapezoidal is half into the distance between a parallel side and sum of the parallel sides. I'm using that. The distance between parallel sides is half into parallel sides is h, and sum of the parallel sides is y naught plus y1. That means our aim is to find out this area. Instead of this, we are approximating it by a area of a trapezoid. That's why this is known as the trapezoidal rule. Why the trapezoidal rule? The name trapezoid is came into picture because we approximated this one, the area, by area of a trapezoid. So this trapezoidal rule has come into picture. So now this one. That means when you are taking this here, what is the error? The error is too much here. You can see. The error is more. Now how to reduce this error? For that one, let us divide this interval into so many subintervals. Instead of taking only single interval, let us divide into so many subintervals, n subintervals. That means you divide this x0 to x1, x1 to x2, x2 to x3. That means we can apply the trapezoid only when your integration is containing only one subinterval, one interval only. So x1, x0, x1 only one interval. x1 to x2 only one interval. x2 to x3 only one interval. Like this, the last interval xn minus xn only one interval. So now in this one interval, what is this? This is the starting point. This is, so this is nothing but here actually. So this whatever is here, it is nothing but integration from x0 to x1. This is y dx. That means y we have taken at the starting point, y have taken at the ending point. That's why y h by 2 and y0 plus y1 is coming. In the same way here, so y at starting point, y at end point. And this will be the difference between them is h, y at the starting point, y at the ending point. Similarly, y at the starting point, y at the ending point. Like this we are having. Now, if I combine all these things, h by 2 has to take common, and y1 is here, and y2 is here, y3 is with next term, yn plus 1 with the previous one. If I correct all those things, we are going to get this. This is called the composite trapezoidal rule. When I apply the composite trapezoidal rule, you can see how the error is reduced with the figure we can understand. This is the basic one. If I take only one interval, the error involved is this one here. This is the error is involved. Suppose if I divide into so many subintervals, I have divided. Like this it is coming. Now what is the error here? Like this is error, you can see. So how much it is reduced? The composites, you can see this. So that's why instead of using the ordinary one, if we use the I'm going for error here. So this is the terrace expansion error of point x0. So we have this. So this is the integration from x0 x1 is this, right? This is we are having in after substituting s. This is our yx. So that means our numeric approximation to do is to between the difference of this and this. That is the error. So I'm taking that one only in the error term. So in the error term of these two differences here. So trapezoid means only with one interval only let me take up. So using the Macron's expansion and everything, we are going to get this, and this is one here. The Terrace expansion of this one, all those things. And here if I take up this, and finally I'm going to get this one here. This is the principal part of this. That means dominating term is it. Next it will be h power 4 or h power 5, something it will be there. Dominating term only will take into consideration. So that is called the principal part or dominating term. So that we have this. So this we are having when we take up in the interval x0 to x1. That means the starting point, the second order derivative we have taken. Now here in the interval x1 to x2, that means when we are not interested only in one interval. We are interested in the all the interval, composite one. In the first interval, what is the error? In the second interval, what is the error? In the third interval, what is the error? Like that, combination of all those things, we should give the error. The total error is that one. So the error in the first interval is this. The error in the second interval is this. Like this, we are having error in the last interval like this, etc. We can get. Suppose if I get this one here, in all these things, minus h cube by 12 is common. Let me take up this y0 double dash, y1 double dash, y2 double dash, this yn double dash. So here, among these values, these are some numerical values. So let us think that here. Some numerical values. Let us suppose that some y double dash of xi, something whatever it may be, is maximum here. So then automatically, each one of them is less than that maximum. So that is having n terms, this is 1, 2, 3, 4, n times we are having n into y double dash I. So this is my error in this one here. This is, so this h cube, I'm writing this one as, so this h into h square I can write. This is h cube. So this h I'm taking as b minus a. And then h square I'm taking up here. So this order of h square is coming here. This is my error. Okay, let us keep this one. So let us go to the next one here. Simpson's 1/3 rule. When we take the Simpson's 1/3 rule, the two intervals are necessary. With the two intervals means, so that means we are having x0, we have the points, two intervals x0, x1, x2. That means we are having the values y0, y1, y2 at these points. The y is defined. That means with these 3 points, we can define the first order derivative, second order forward difference, second order. So up to second order only we can utilize. So we have used only 2 terms in this one, approximation. How many terms we can use? Based on that we can use. So only 3 terms. So only up to second term only. And then we have taken up, finally, this is the one. That means in the interval, this is the approximation to integration from x0 to x2. This is yx dx. So here the points are, this is the one. That means h by 3, that is h by 3, the step length. And here x0 to 2x2, x2 minus x0. This is, we are having 2h, 2 intervals we are having, 2 intervals, 2 sub-intervals we have divided. That's why we are getting like this. So y at the starting point, y at the end point, and middle point multiplied by 4. So middle point is x1 somewhere here. So between x0, x2, this one. So like this. So always it is better to use the composite in place of the usual one. So just like in the trapezoidal, here also if we apply the composite, it will give the less error. So let us go for the composite one. So composite if I take, so this is the one. And here the second interval, this is the x0, x4. This is for x4 to x6. Like this we are having. And this one I'm having this here. Now collecting like quotients we are having like this here. So this one. Now in this one, if I take the error term, what we are going to get? Proceed the same direction. So if I get this one and everything, finally this is the one. The Taylor's expansion around the point x0 and everything, if I take up this one. So finally the error is this, error in this one is this one. So error is this. So finally we are going to get, so after using the Maclaurin's, the Taylor's expansion for this, this is y0. This is y1 means y of x0 plus h, and y2 means y of x0 plus 2h. So if I apply the Taylor's expansion for this is also Taylor's expansion for this, and then collecting the coefficients and everything, finally we are going to get like this here. And then collecting the like coefficients and everything, we are getting this one here. You can see. Okay, finally, this is the one. Now here h power 5 is coming. So this is in the interval x0 to x2, x2 to x4, and x4 to x6, like this here. This is not the total error in this one. This is the one. Finally, this is the one, h power 5. This is the one we are going to get. So here, if we use the trapezoidal rule, we are getting only h square is the error. And here, with this one, we are getting h power 4. So this is a better one. When h is small, based upon the same h, here also h only, here also same h. So this is the better one. But here we are getting 1 by 90 is a factor. Okay. Now in the same way, if we proceed with the 3/8 rule, that means if we divide into 3 points here, that means we want to evaluate with the 3 points. That means we want to evaluate like this here, integration from x0 to x3 yx dx with the 3 points. So here with 3 points means x0, x1, x2, x3. With these points, we can have y0, y1, y2, y3. And then with these points, we can have the delta y0, delta square y0, delta cube y0 also. So let us use up to third order forward difference interpolating polynomial, and then we can get that, and then apply, and then substitute lower limit and upper limit and everything. Finally, we are going to get this one here. So now if I look at this here, composites, if we apply, finally we are going to get this expression. So in this composite here, the error, once again, if I calculate here, this is the one. Finally, so 3 by 80, this one here. This one. You can see with the trapezoidal, we got h square. With the trapezoidal, we got h square. This is with the trapezoidal. And with the Simpson's 1/3 rule, we are getting minus 1 by 90 b minus a into h power 4. This is y fourth derivative xi we are having. And whereas here, this is 3 by 80. This is minus 3 by 80. That means same here, b minus h power 4. Here also b minus h power 4. Here also b minus h power 4 y power j is coming. But whereas the factor, here you can see, this is 3 by 80 is a factor. And here 1 by 90 is a factor. When the same factor is multiplied by this is a less than means upper bound. Here upper bound is less. Here when we multiplied by this upper bound, absolutely, error is always absolute. Even though the minus 10 is here, it can be absolute, we have to take up. Because we don't know what is the value of this one here. It may be positive or negative. That's why I did not take this one here. In general, error means it's absolute sense only. So 3 by 80. When we multiply the same factor with 1 by 90 or for 3 by 80, whichever is giving less, 1 by 90 gives the less. So it is better to take up. That means whenever the n number of intervals are there, this n number of intervals can be either it is even or odd. Even. So whenever we take up the even number of intervals, Simpson's 1/3 rule is always better. Suppose if it's an odd number, we can divide, we can take it into 2 categories. It is a multiple of 3 or not a multiple of 3. Odd number, not a multiple of 3. Suppose if 9 is taken, yes, it is a multiple of 3. We can apply. Suppose if 7 if I taken, it is not a multiple of 3. Then we have to apply this one. That is, it is not even. Simpson's 1/3 is applicable only when even number of intervals are there. Suppose if it's odd number of intervals are there, if that odd number is multiple of 3, let us apply Simpson's 1/3 rule. And if it is not a multiple of 3, let us go ahead with the Simpson's, trapezoidal rule. In this case, it is a trapezoidal rule. That means which one we have to apply. That is also more important. We have divided that given interval into so many subintervals. Whether we have to use all the three are available with us. Trapezoidal is available. Simpson's 1/3 is available. Simpson 3/8 is also available. Out of this, which one we have to use? That means the given interval A to B, we have divided into n subintervals. That depends upon n, whether it is even number of intervals or odd number of intervals. It is that even number of intervals. Let us use the Simpson's 1/3 rule. This is the Simpson's 1/3. Simpson's 1/3 we can apply. If this is the case, that means this is the case. Then Simpson's 3/8. And if this is the case, then let us use the trapezoidal. Like this we can divide. So that's what I have written here. So it is clear from the expressions, the error terms is divided into even number of intervals. It is better to use the Simpson's 1/3 and this one here. Okay. Sorry, is this okay? Errors and everything, sir?
Yes,
Yeah.
actually.
So
It's
now
very
let
good.
us take this one here. Just I'm taking first a simple example, and then I will go to this one here. So here, if you look at this here, so we have to evaluate the integrand, that is 1/1 plus x square at various points. We have divided into n and 8 intervals. It is better to use the Simpson's 1/3 rule we are getting. Our aim is to find an approximate value of pi. What is this actually? If I take up this is nothing but integration from 0 to 1. This is 1/1 plus x square dx. This is nothing but tan inverse x between 0 to 1. So tan inverse 1 is pi/4 and this is tan inverse 0 is 0. That means your integrand this is pi/4. So that means your pi is equal to 4 into integration from 0 to 1, 1/1 plus x square dx. That's what we have to take up. So now if we was in a position to evaluate this, okay, fine. Or if we're not in a position, let us take up the by numerical approximation and get that. So here this is pi/4. So if you multiply this, this will be, let's see, actual value. You can see this up to 3 decimals. After, if you make it only 4th decimal, if you looking at the 5th decimal place, if you round it off, almost an exact one we are getting here. You can see I maintained only 4 decimal places. What are 50 decimal places? I'm looking at the 50 decimal. I made it round off the 4th decimal place, and I have maintained. And finally, I'm getting the exact one. You can see. Our aim is to look at finding the approximation. Almost all very close. We have got it. That is the advantage here with the numerical integration. In the same way here, this is the one sin x by x. If I take the sin x by x also. So when x is equal to 0, 0/0, enrichment is coming. So we cannot get. So then what we have to do? Let us take the limit extends to 0. So limit extends to 0, sin x by x, that we know it is 1. Yes, it is. For the rest of the things, it is available straightforward. And then go ahead. But the only thing is the argument x must be not in the degrees mode. It should be in the radians mode. With that, we calculated and everything. Finally, we are getting this. Similarly, we can get this one here. Simpson 3/8 rule, 9 intervals, 10 nodal points. That means 10 points. With 10 points, how many we can get? 9 intervals. That 9 is a multiple of 3. So let us use the Simpson's 1/3 and we are going to get this. Like this, we can get. So velocity, if you want to get the velocity, what will be this? Here. So the velocity v is given. Now we want to fix at the intervals of time. The moment starts from rest. For estimately the distance traveled by covered in 20 minutes. Because it is started from rest, initial velocity is 0. That also I'm taking the picture. Here it is not given. The v at t is equal to 0 is given. But from the given data, it starts from rest. And it is starting from rest means initial velocity is 0. So that let us take up that and then proceeding. So 10 intervals and everything, then we can get that. Now even number of intervals, we can apply the Simpson's 1/3 rule and we can get that. Like this we can get. So here area bounded by the curve, we know that the formula we have to use and get this one. This one. We can get this. So here the integrand is pi by square. You can, once if y is available, and you can get the pi by square also. Pi by naught square, pi by 1 square, pi by 2 square. All those things you can get and you apply that. And we can get that. Just applications, how to do. And here we want to find the estimate the length of the curve. What is the length of the curve? The formula is this. Now from this, what is this here? The y is equal to x cube by 3. Now what is dy by dx from this? It is x square. Now If I apply this one here, I'm going to get this one as integration from 0 to 1, the square root of the 1 plus x power 4 dx. But for this integrand, it is very, very difficult to get. But numerical approximation we get very easily. So let us use that and proceed. How many intervals you are taking and everything, you can see that and proceed. That's all. Okay, now let us look at that Romberg integration. How many intervals we have to take up? Sir, I have to take up 4 intervals or 6 intervals or 10 intervals, or sometimes I may take 20 intervals. Suppose if I take 100 intervals, I may get a better result. So shall I go for that? No. So there is no limit for that. Even if you take up 100 intervals, next you may say, sir, with 200 intervals, I may get a better result. Where is the end for that? So due to that here, let us look at this one here, Romberg integration. With the 2 different intervals you take up, with the n1 intervals you find approximation, with the n2 intervals you find approximation, with the n1 and n2 you take the either with the one either by trapezoidal, both of them you are evaluating by trapezoidal, or both of them you are evaluating with Simpson's one-third rule. One of them, both you evaluate with the same rule only, not one with trapezoidal, one with Simpson's. Not, let us not do like that. Both of them with the n1 intervals, with the n2 intervals also, let us approximate with the same trapezoidal or same Simpson one-third rule. Let us look at that here. Suppose if you are evaluated with the trapezoidal, Romberg and with trapezoidal, that means using with the n1 intervals some approximation I1 is there with the n1 intervals. With the n2 intervals, we are having the approximation with I2 here. Now using these approximations, I1 with the n1, I2 with the n2 intervals, using these 4 values, now I want to get the better approximation for this I than this one. If instead of taking some other one, go on refining the intervals and intervals, just with a simple formula, we can go ahead that. Let us go for that one now, Romberg integration. What is this one? So here with the n1 intervals, let h1 is the step length. Let us think that this is the error we are getting. Now with the n2 intervals, let h2 be the step length. This is the one here. That means here this one. Now E1 is this. So in this one, whatever this b minus a by 12 and y double dash I, it is common here in both the terms. Here you can see. Let us take that one as k here. B minus a cube, this one as k here. Let us take up that one. So now this will be I1 plus this one. So k plus I1 plus I is equal to I1 minus this k by n minus h1 is nothing but what is h1 from this b minus a by n1. So let me substitute that one there. So these also h2 is equal to this one. So after that b minus a cube by 12 into y double dash I. Here also b minus a cube by 12 y double dash I. That I am taking it by k. So this is k by n1 square. This k by n1 square. So this is I is equal to I1 plus E1. This I1 plus E2. So that I have taken here. So this one. Now from this, what is the value of k here? This is the expression of k I am getting. And this expression for k2 from this expression. Now in both the same k I am having. Same k. It is not a different k. So same k with 2 different. From this, if I get the value of I here, I'm going to get this here. Finally, I'm going to get this. That means you are getting a better value of I when you are using all these 4 values. Similarly, with respect to this, you need not go on refining. Refining is not necessary. How many times you will refine? No end for that. Instead of that, you take just 2 more, 2, 3. You take up 2 more, 2 times or 3 times refine. After that, you just go for better approximation for I with the trapezoidal rule. That is better. Just 2, 3 you take up and proceed. That's more than sufficient here. Now with the Simpson's one-third rule, same logic if I apply and everything. If I take up, this is error. And then if I take up this one here. Now finally I'm going to get this one here. So this is the value of I. All the time with I1 and 1. I1 with n1 intervals. I2 with n2 intervals. All those 4 values we are using. This is the better one. If even number of intervals, this is the better one. With odd number of intervals, it is a multiple of 3, multiple of 4. That will be. So with the Simpson's 3/8 rule also, we'll get the same thing here. Same thing. The Simpson's 3/8. Suppose if 12 is there, 12 number of intervals. So it is a even and multiple of 3. It is even number at the same time multiple 3. If it is taken even, the error will be with the same error with 1 by 90 here. And whereas here with Simpson's one-third rule, in place of 1 by 90, we are getting 3 by 80. That upper bound is more in Simpson's one-third rule. When upper bound is more means when it is closing, your error is close to the upper bound, accuracy is less when compared to the Simpson's one-third rule. So always it is better if it's always let us take up even number, even though it is multiple of 3, let us take up Simpson's one-third only. Let us not use Simpson's 3/8. That is one point here we have to notice. Now here another thing here. So like this we have to go. So many things I have taken up and everything, and then I'm one small example, and you can see this one here. Here with 2 intervals, I'm getting this one is with this one only. Now you can see. This is my error. And here with the 4 intervals, I'm getting this. But actually, earlier we got this value with 8 intervals. Shall I go to the 8 intervals? No. Just use already we got this one. Just use that and then get this. When I want to take up the 8 intervals means 8 times I have to do the function evaluation. And here also, whatever this is here, y at 0, y at 0.5, y at 20, these are also available here. You can see only extra 2 only I'm using. So I'm not using a new ones, functional values and everything. Already if I taken this, it's a part of this only, the values and everything. So if I take 8 means another 4 points I have to take up. So instead of that, just use these values already. Just get that and almost everything. Instead of 8 function values, with 4 function values, we are getting this. Computational complexity is coming less. The same accuracy is more, with the computational complexity is less. You can see. So like this one.
So would it be possible that means this will give means generally in our programming and all this we just keep on increasing the numbers and numbers, and we say we think the more is the number and better would be the answer. So I never actually use this thing actually in my all computational actually.
This is better. Instead of going for
so due to this I could have saved my computational time by hours actually.
Yeah, that's what I'm going to say. That's why all my concentration is this one only.
This is it's very good thing we came to know actually. Yeah,
this is a better one. You can see. I will share. I will share entire this PDF point. Whatever this is, PDF I copied here. The PDF I will share.
Because in engineering we always end up with some differential equation which need to be integrated only.
Yes.
So in that case we always focus on numbers and numbers and numbers.
Yes. You are go on diminishing the step length, and finally at some point you say that there is no much difference is there, so let us accept that. But by
that's
that
what
time,
I wrote in my paper also.
It is not required. It is not required. It is not required.
Okay.
Instead of place of this, you can say that the Romberg integration, and we can go ahead.
Oh, good.
That's good. That will be better.
Yeah, thank you, sir. Continue.
Yeah. So another thing point here is that some more interesting point I want to bring here. Here, trapezoidal rule gives the exact when the integrand is linear, exact. That means whenever you take your integrand is quadratic polynomial or higher order polynomial, then it always, even if you take up the 100 intervals, it is an approximation. It is never be exact. That is one point we have to notice here. Trapezoidal, even if you take up the interval, 100 sub-intervals you take up, but still if you apply the trapezoidal rule, it is a linear, it is approximate, it is never be exact. That means with 100 intervals, how many function evaluations we are doing? 101 function evaluations we are doing, we are getting approximation. Okay, now with the same 101 evaluation, if I use the Simpson's one-third rule, same 101 points only, but here it is exact up to quadratic only. From cubic onwards, if the integrand is cubic, it is an approximately. That means even with 101 function evaluations, it will be approximation only. It is no more exact. Now I'm bringing to that. That means 101 function evaluation we are doing. But even then we are getting from the integrand is cubic degree, fourth degree, fifth degree, like this. We are getting all the time. We are getting only approximations only. We are not getting exact value. But our interest is that we should not get any error. That is our aim. If possible, very little error. If it is excusable, a little error we want to get. How to reduce our computational effort, just like here, what we have done in the Robrek integration. Is there any other alternative is there? Yes, it is available. That is the Gaussian quadrature formulas.
Yeah, I was just saying to that only because I use the numerical integration by Gauss quadrature.
Yeah, Gaussian quadrature.
And
I'm bringing that one only. I'm bringing that one only.
yeah, 2 point and 3 point Gauss quadrature
Yeah,
give the perfect answer.
with the n points, we are going to get up to n minus 2n minus the degree exact.
Yeah.
2n minus with the n points, 2n minus the degree exact we are getting. Okay, that I want to concentrate. Here you see numerical integration based on the quadrature. Based on the quadrature. Generally, it will be like this, where wx is greater than 0 and a to b. Here it is a weight function. This is the interval. Okay. Now we assume that wx and wxfx is integrable. With that understanding, otherwise, if it is not integrable, numerical value will not come in the picture. Even if you exact one may be there, or sometimes we have interest to find out the approximation. First of all, it must be integrable one. If it is not integrable, whatever the approximation you get, it is a garbage value. We never say that it is a true value or approximation due to true value of this integral here. So that it should be essential condition here. They should be integrable, something like that. So now let us say that this is one. The points are the points in the open interval. Earlier, at the endpoints also we have taken x0 and xn. We have taken endpoints. Here, all these are the points we are taking inside. So these may be generally. So how to choose and then select. You evaluate the points at this particular point and this one. Just you take the integrand without this wx and then just evaluate at these points and then multiply it by this lambda k. How to get that? Let us use that. It's exact up to 2n times 1. Suppose if your integrand is a cubic polynomial, and if I use the Simpson's 1/3 rule, 101 evaluations I have taken up, 100 intervals. Even after 100 it is approximately. But suppose if I use n is equal to 2 with this one, so 2n minus 1, it is 3. That means up to the third order it is exact. But just with the two valuations, you can see the function where x1, x2, if I'm using, with the two function evaluations, I'm getting the exacts. Whereas 101 function evaluations, and whereas just with the two function evaluations. But I'm getting exact. There with 101 evaluations, it is the approximation. And whereas it's just with the two function evaluations, it is exact. Now you can see. So that is advantage. So even if I take 3 points up to 5th order, it is exact. If I use the 4 points, then it will be up to 7th order, it is exact. So that is advantageous Gaussian quadrature. So what if there is some limitation is there to use the Gaussian quadrature? We have to transform some transformations and everything. We cannot use just it. And another thing is that how to choose these points and how to get this lambda case, how to choose the points x case and how to find out this lambda case. That is more important. Once if you are able to get this x case and lambda case, problem becomes very, very simple. So how to do that one? Let us take up that. There are 4 different types of formulas are there for this one. Depends upon this ranges of a and b and this your wx, ranges of this wx and a and b here. Okay, so 4 different formulas: Gauss-Legendre, Gauss-Chebyshev, Gauss-Legre, Gauss-Hermite. All those 4 I'm going to concentrate. With that I will stop. Just with 10-15 minutes it will be over. So now if you take up this one here, so in the Gauss it will be -1 to 1. Your wx is 1 and -1 to 1, and this is the one. Where we are going to get x case? These are nothing but the Legendre polynomial, nth order zeros. That means the zeros. That means if I take up p and x is equal to this is nth order polynomial here. If I take the roots of this nth order polynomial, that will be your x case. Zeros means it is nothing but the roots. Roots of this one are called the zeros of this. So roots. So these are nothing but zeros of p and x. This is called. So that one. So this lambda k is going to be given by this. And how to get this Pnx? Let us use the Rodriguez formula and get that. Very simple. Now, if I take the Rodriguez formula with n is equal to 0, this is the one, n is equal to 1, P1x, P2x, P3x, and this P4x. If I take up this P2x here, what will be this? Equal to 0. Plus or minus 1 by root 3 is the roots. And if I take this here, 0 is one root, plus or minus root 3 by 4 is another roots. Here you can see minus plus or minus root 3 by 4. And if I apply that in the lambda k formulas, these are the weights I'm getting. Suppose if I take this 3-point formula up to 5th order, it is exact. You can see. Just if I use, these are the weights, lambda k's, and these are the zeros. And if I 4th order, 5th order, 6th order, the polynomial is like this. It will be just like this. Here. What only the thing is that what is the here the restriction is integration is from -1 to 1 fx dx. In general, a to b will be there, fx dx. What is the guarantee that a will be your -1 and b will be +1? There's no guarantee. So let us transform this interval to this, or it will be some g of t dt. Whatever it may be, it does not matter. Equivalent one I want to get where g of t. That means the expression, whatever this is there, when it transforms, equivalent expression, we brought it. Then it really can use that. So suppose if I take up AB is the general interval, and this -1 to 1, just use this transformation, just a very, very simple transformation. Just use this transformation, we are going to get this. Now here, dx is equal to this one here. Now if whatever is there, x you substitute here, your dx would b minus a by 2 t. And then your, when a is equal to, when you substitute x into a, t will become -1. When b is equal to a, when I take up, the t will be 1. And then it will be substituted, and then we can get that. Now, the Chebyshev, it will go into given by this one only. Square root of 1 by 1 is double x, and lower limit, upper limit is this one here. So this will be. Sir, for same thing, if you want, yes, you can take up the Gauss Legendre also, but only thing, the integrand, this will become easy. This will become the integrand. Their evaluation becomes a little bit more effort we have to put in the computational. But that effort will be less. Without this factor, we can have this gfxk and just substitute and get that. Both are will give the same thing. Either you can do by that formula or this formula. Does not matter. Both will give the same results. Same accuracy, same thing we are going to get. But computational effort will be less when your fx is having of this form here. Integrand is of this form. If the integrand is not of this form, without having the factor of this 1 by square root of 1 minus x, then it is better to use like Legendre. Otherwise, let us use this one here. The same thing. Where these xk's are given by, this is this one here. Xk is your cos of theta k, where theta k is this, and your lambda k is uniformly pi by n. And then you can go ahead and this will be. Let us take some example for this. Find the value of a using 3-point Gauss quadrature. Here a is equal to 2, b is equal to 3. If I get this, and here I'm taking up, just I'm using the formula, I substituted, and then finally I'm getting this one. So we're your x is equal to half of t plus y. So dx is equal to half of dt, just if you substitute and everything. And finally I'm getting this. So this including this half and everything. So this is your becoming the integrand. This is your f of t. And then apply the 3-point formula. It is there. Just get that. It is up to 5th order polynomial, it will be exact. Suppose if I take up this one here, up to 5th order polynomial extraction. Generally, we never go up to beyond the 5th order. That will be more than sufficient. If you want to approximate by polynomial expression, something like that, 5th order will be sufficient, more than sufficient. So that will be sufficient. Or if you want more, you maintain another 1 point more. That is up to 7th order. Or if you take one more point, 9th order, that will be more than sufficient. Okay. So another example, here this is the one. Just if I take this one here, let us look at this one. Just if I apply this, so this one I'm getting. You can see. So here, whatever I'm getting here, this factor of 1 by 1 minus t square is coming. R in plus xt, that's the only difference. Only variable difference only. You can see my f of t is this one now. This is the one. If I want, I can use entirely taking this. Legendre polynomial also I can use. Legendre quadrature also. But in place of this, Legendre I have to calculate even for this one at every point. But here it is not required. Just if we take that will be sufficient and it will give the results here. You can see like this way I'm going to get. Now one more. Sometimes we are going to get integrals will be 0 to infinity. These are not finite. Infinite integrals we are going to get. Then how to get the infinite integrals? The approximations. There your function is like this here. Suppose if the weight function e power minus fx is this one, then you can apply where this is the zeros of the Lagrange polynomial and where these Lagrange polynomials are given by like this here. Sorry, here the factor is not there, then how to proceed further? Suppose if some g of x is there or some expression here that integration from 0 to infinity, some expression sine 2x by this is 1 plus cos 3x dx something is there. Suppose if I want to evaluate, let us think that. Sorry, here no e power minus x is there, then how to take care of this? People will ask, but in interval is 0 to infinity. Then in that case, if I nothing wrong in that, if I take like this, anything wrong? Nothing wrong. Now I can take up this one as my fx. Okay, take this as my fx and then proceed. I'm going to get this. So then we can proceed further like this here. You can see. So very, very simple. Now, sometimes what happens is that the interval is from minus infinity to plus infinity. If it is your integrand fx is an even function, then you can divide this, you can convert it 2 into integration from 0 to e power minus x square fx dx. And you can evaluate it with Gauss, Lagrange, whatever is there, that's okay. But here it is not even function. It is not even function, neither odd function. If it is odd function, it will be 0. Okay. Now it is neither odd, neither even. Then how to get that? So then we can let us go for this one, numerical approximation. It will have some value. For this one, it is a Hermite polynomial we are going to get, and we have to get Hermite polynomial is this and this one. All these things are very, very simple ones. Suppose if it's not there, you just, as in the previous case, if some expression g of x is there, you just multiply e power minus x square, e power x square, g of x. So take this as your fx and then proceed further and then get that. Fish. That's all. It's a very, very simple one. Manipulate. Just you bring this weight function. This is the one. This is more important. Unless this is there as a factor for the integrand, we cannot apply the Hermite quadrature formula. How to bring that? Just use this simple and go ahead. Nothing wrong in that. Always we can go ahead. So simple examples I have taken here. So for this one, so next with that, that is my last slide. So simple example. This is 0 to pi by 2. And if I want, I can go ahead with the Lagrange, because these are the finite intervals. I can go for Legendre polynomial and go ahead and get the result. Nothing wrong in that. But instead of that, just I want to take the transformation. Sin x is equal to e power minus t. This is with experience it has come. Suppose if people are not having go instead of going for this, you can go ahead with the Legendre. Nothing wrong in it. Legendre also can be applicable here. Legendre. You can apply and get the results. Nothing wrong in that. Suppose if I use this one with experience it come, then the integral is transferred to be, you can see here. So my integration is this here. You can see. This is my integrand. With minus t by 1 plus e power minus t is my integrand. Then you can see that. So this is last Hermite Lagrange. If I use 4 point, I'm going to get this one here. This is the one. And here it is a straightforward case. Like this I can get.
So this is the limit minus means infinity to plus infinity. We will not be in the position to convert it to the -1 to 1.
It's not required. -1 to 1 is difficult. Suppose if you are in a position to
Yeah,
-1.
yeah. No. I'm just talking that if we can convert it, then we can use the Legendre's Gauss quadrature, right, sir?
Yeah. No. Here also, this is also quadrature only. This is also quadrature, but Hermite
Yeah,
quadrature. Hermite we are using. Instead of Legendre, we are using Hermite. In this case, if with some transformation, or substituting the value of x or something, if you could able to transform to -1 to 1, okay, fine, very good, welcome. But if you are not in a position, then go ahead with hermite.
Correct, correct.
Are we in a position to convert in this position or not? That is more important. If you are not in a position, then we have to go with hermite. That gives the results.
Yeah, it's better actually not to convert and use it
Yes,
directly. Actually,
yes,
this is
yes.
many
That's
times
what
better.
my point is. That
Mm.
one only.
Yeah, yeah.
My point is that only. Even this factor is not, we can bring it. I told you, multiply e power minus k, e power x square, the integrand and get that. Simple. And go ahead. Sir, this is the one I want to present, whatever is there. You just, now
Yeah,
open for,
actually, yeah, thank you very much. It's very interesting one, and learned a lot from here because I do used to do integration actually. Differentiation, numerical, I generally don't do it, but I used to do want to do for my drawing data actually.
yeah,
So where I have several of data actually, thousands of the data points. So previously I was doing a sluggish mistake. I am just taking x2 minus x1 divided by t2 minus t1. That can be the differentiation actually rate, but it's not a good thing, right? So therefore I was not getting something correct.
yeah, that's right. Because there, the computation company accuracy is also more important. You whatever the values you are taking, they may not be that much accurate. Now with this, retaining the more terms, and if possible, if you are in a position, let us take the more terms, then more accuracy will come. Or even this
Yes, yes.
and all those things, transformation, everything, if possible, or a Simpson's one third rule, whatever, or Romberg integration, you can apply and get that. That is better. Instead of refining so many times.
Yeah, because in our experiments, mostly we get let's say time versus concentrations of our data.
Mm.
We are supposed to calculate rate. So rate is practically just nothing but dc upon dt actually.
Yes, that one only.
So if we are calculating that dc by taking two consecutive point and two consecutive corresponding times, so we may not end up with the correct rate actually. So we have to take a proper the
Yeah,
differentiation formulation for the entire the data points only.
yeah, yeah, yeah.
So any question from the participants, they can ask actually.
And even that, the forward difference, backward difference, it is not a much, formulas also very easy to remember and everything we can get that. Suppose by writing the
Right, right,
programming,
right.
if we generate those differences with the given data values, then better. You can apply and get their values.
Any other question from any participants?
Sir, interactively, I made the presentation, everything, instead of just going.
No, no, actually,
Yeah.
it was actually really a very wonderful theory followed by explanation and applications actually. Rest of the part actually, see, most of the time we don't know the technique. So if we don't know the technique, what program we will the right actually?
No, I may not taken any engineering applicated examples and everything, but generally how to use. That's only my point. Being a mathematics
Yes,
professor,
yes, yes.
mathematician, my point is how to use in your engineering
Correct, correct,
application. Yeah,
correct.
that is more important concept. That's why the mathematicians and the engineering people should go together. Then more practical application, more results will come out. It's interactive.
Yes, yes,
It should not be engineering people only should do the work and mathematics only should do the work. It's not like that.
yes, actually. So actually, to interpret the data and all this, you need the strong mathematics
Yeah,
side
yeah.
actually.
Yes.
So just to get the data and for the prediction, you need a mathematics actually.
Yes.
So any question from any one of the participants, they can ask actually.
Only I went in a little bit mathematical way. That's only the
No, no, no. See, it why the mathematics? So this should be done in that particular way now only.
yeah, only some rigorous mathematics may be there. Anyway, I'm sharing. I will
No,
send to
no.
you by mail this presentation. I will send to
It
you.
was need actually. Without that, how can you do it? Because this
Yeah,
is
yeah.
the numerical
I think
integration
you
and
might
the
have recorded
differentiation.
also. Anyway, without all these things, I will send.
Yes, yes,
Yeah, you
yes,
have
yes.
recorded this one. It is there. But even then, the usual without this marks and everything, whatever points I have written with pen and everything, they might not be there in my original PDF file. So that I will send to you.